We look at the second common type of data structure, namely the linked list. We see how it can be represented logically and physically. And we look at an application of linked list where linked lists are used to manage dynamic memory. I want you to execute this code and get the memory address because the memory address will be different in different machines. When I executed in my machine, the address of A was at 11342848, B at 824, C at 856, D at 888, and E at 968. The memory is depicted on the right hand side, and each block is assumed to hold 4 bytes of data, which is the number of bytes required to store an integer. A, B, C, D, and E are lists composed of many integers. A stores 4 integers, B 6 integers, and so on. The empty spaces are represented in black. B is a list which is composed of 6 elements. Now a new problem statement arises wherein B requires 9 elements in it. So we need to add 3 elements in B. When we try to reallocate the space for B using the realloc statement, we try to change the number of elements from 6 to 9. Realloc tries to find 3 spaces immediately following the 6 elements of B. But in our case, it is not possible to increase the space in the current address because there are only 2 free blocks available and B requires 3 more free blocks. So when contiguous spaces are not available, the memory address of B is relocated to a different place where it can find all the 9 elements. But what if we cannot find 9 contiguous blocks of memory? In this case, we are unable to allocate it any space. This is because Mlog and realloc expect contiguous blocks of memory space, which is the requirement of any array. Arrays require contiguous blocks of space, and when there is no contiguous blocks of space available, they are unable to allocate space to the array. The entire array cannot be allocated any place even though there are free blocks scattered in the memory. The obvious solution is using what is called as a linked list. The linked list is a data structure in which the elements are stored in such a way that the value of the element and the address of the next element in the list are both stored. Let us have a logical view of a linked list. When we were talking about Mlog, we were trying to explain the concept of an array where every element in a list required contiguous blocks of space. We are moving from the concept of arrays, which requires contiguous blocks of space, to a linked list, which does not necessarily require contiguous blocks of space to store the different elements in a list. B is a list of 6 integers, and the first element in B points to the second element in B. The second element points to the third element. The third element points to the fourth element. The fourth element points to the fifth element, and the fifth element points to the sixth element. Because there is no compulsion that all the elements must be in contiguous locations, when we ask 3 additional space, or when we want to include 3 more elements in B, the 3 blocks of space can be allocated anywhere in the memory. The next block is allocated at the next free space, which can exist anywhere in the memory. And so the 6th element points to the 7th element, the 7th element to the 8th element, and the 8th element to the 9th element. The 9th element explicitly states that it is not pointing to any other element. Logically, we say that one element in a linked list points to the next element in the list. But physically, what actually happens in the memory? The linked list is such that each element in the list is composed of 2 parts. One is called as the data part and one is called as the address part. B is a list consisting of 9 elements and the data values are 1, 2, 3, 4, etc. up to 9. The amount of space required to store an element in B is now different from the way we store it in an array. When we stored it in an array, when we store the entire B as an array, we allocated 4 bytes for each data item. But when we use the concept of a linked list, one data item is composed of the data value and the address. So it takes 4 bytes to store the integer and another 8 bytes to store the pointer value. And 2 is stored at the location 836. 1 stores the data value 1 along with the address at which we find 2, namely 836. So totally 12 bytes of space are required to store one element. The second element 2 is at the location 836 and it points to the next element in the list, namely 3. And 3 is stored at the address 848. So the second element stores the data value 2 and the address of 3, which is 848. The third element stores the address of the fourth element. The fourth element stores the address of the fifth element. The fifth element, the address of the sixth element. The sixth element, that of the seventh element. The seventh element, the address of the eighth element. And the eighth element, the address of the ninth element. The ninth element is the last element in the list, and so we explicitly say that it does not point to any other memory location by substituting the value null in the place of the address. The first linked list depicts the logical view of a linked list as if the first element points to the second element, the second to the third, and the third to the fourth, and there is a null pointer in the fourth element's address part. But the second part of the diagram shows the way the elements are actually stored in the linked list. 1 is stored at the address 48, 2 is stored at the address 52, and the address 52 is stored along with 1. 3 is stored at the address 78, and it is stored along with the data value 2, and so on. A good place to apply linked list is for dynamic memory management, where we can make use of a linked list to keep track of the free and the used spaces. When we execute an Mlog statement, it takes blocks of elements from the part of the memory called as the heap. For the purpose of illustration, let us assume that the heap is composed of 1000 blocks, each accommodating 4 bytes of data. So the amount of free space at our disposal is 40,000 bytes. And the starting address of the heap is at the location 342848. To represent the free space, we use a linked list, which is composed of 2 parts in the data part and 1 address part. The data part is composed of 2 values, one showing the starting address of the free space and the second denoting the number of bytes in the free space. And the address part has the address to the next free space. So when A is allocated 4 blocks of data, 4 into 4, 16 bytes of data have been allocated to A, and now the free space starts from 342864. Still there is only one block of free space starting at the location 342864, but the number of bytes available is now reduced to 39984. And so the linked list still has only one element in it. Now another Mlog statement is given which asks for 6 blocks of integers. B is allocated 6 contiguous blocks at the location 365824. But now the number of free spaces become 2. One free space starts at 342864 and the second free space starts at 365848. The amount of free space in between 365824 and 342864 is 22,960. The first element in the list depicting the free space now says that the free space starts at 342864 and the amount of bytes available is 22,960. The second element in the list starts at the location 365848. What is the amount of free space in that? This can be calculated as follows. The total space is 40,000. I have used up 16 bytes for A, 24 bytes for list B, and I have also got a free space in between A and B, which is 22,960. Now the remaining space is 17,000, and that is the free space available at the location 365848. This is depicted in the free space linked list. Now the list is composed of two elements, and the first element, which is the first free space, points to the second element. This data structure, which is a linked list, is maintained in a separate space in the memory. So there, the first element of the linked list is stored at the location 200000, and the second element of the linked list is stored at the location 10045. When an Mlog statement asks for 3 blocks for C, list C is assigned at the location 365856. Now, 8 bytes of data are free in between the space allocated to list B and list C. Now, we have 3 separate free spaces. One at a location 342864 for 22,960. The second at 345848 for 8 bytes, and the third at 365868. And the remaining space is 16,960. Continuing in this manner, draw the linked list that shows the different free spaces when A, B, C, D and E are allocated 4, 6, 3, 16 and 12 bytes at the locations given in the slide. This results in a free space linked list. The list is composed of 5 elements depicting the 5 different free slots that are available. The first free slot is at 2864 for 22,960 bytes. The second at 5848 for 8 bytes. Next at 68 for 20 bytes. Next at 5952 for 16 bytes. And the last at 6016 for 16,832 bytes. Thus, we have seen how linked lists can be used to manage the dynamic memory in a heap.